A good interface of an ADT is not only about being clear of what it can do, but it's also about what it cannot do. Constraints and limitations are what enable optimizations. By limiting what an ADT can do, you can prioritize certain operations, allowing you to optimize for them. As an analogy, a restaurant that can serve every kind of cuisine and has thousands of menu items is probably going to be less efficient or tasty than a restaurant that focuses just on French cuisine that limits itself to 10 menu items. And speaking of food, food is served on plates, and plates are stacked on top of each other. So today, we are going to talk about the stack ADT. Two of the most studied basic ADTs are the stack and the queue, because they are kind of like two sides of the same coin. At a high level, a stack is a LIFO, aka last in, first out collection of elements, while a queue is a FIFO, aka first in, first out collection of elements. Just like a stack of plates, the interface of a stack is restricting. You can add elements to the stack, but you can only remove the element from the top of the stack. We call these operations push and pop, as you can push elements into the stack and you can pop them off the stack. A stack can be implemented with an array or a linked list, just like how we did with the list ADT. And today, we'll be exploring the pros and cons of implementing the stack with each of these data structures. So before we implement it, let's formally define what a stack is and what the interface is. So the stack is a collection of elements, just like the list ADT. Let's initialize a stack, shall we? However, the stack only has two main principal operations: the push, which adds an element to the collection, and the pop, which removes the most recently added element, or if you think of dishes, which pops the dish at the top of the stack of dishes. Okay, let's add a few elements. Let's push the number 4, 7, and 3 onto the stack. Great. Now let's try to pop an element off. Which number do you think will pop off? Yes, that's right. The element with the value 3 will pop off because it's the element that was last in, so it is first to come out, hence LIFO. Usually, for stack ADTs, the pop function also returns the value of the popped element. So just keep that in mind when implementing your stack ADT later. Let's add two more functions to our interface, top and isEmpty. Top will allow you to get a peek on the last element you pushed in without having to pop it. And isEmpty will just tell you if the stack is empty. So for example, if I now call top, I would get the value 7. And if I call pop, I would still get the value 7. But if I call pop again this time, I will pop off the 4. And then pop off the 9, then the 4. Now, if you call isEmpty, it will return true because the stack is empty. Now, you might have noticed that you can't do as much as the list. For example, what if I want to pop off the first element? Well, you can't. That's the point of a stack, is that you have to follow its rules and interface. And those restrictions will allow us to optimize our implementation. If you want to pop off the first element, you'll have to pop off all of the elements on top of it before being able to pop off the first one. Okay, now you know what a stack is, let's think about its different implementations and its pros and cons. This will train you to think of trade-offs whenever you write code. First, let's see the implementation of a stack with a fixed size array. The stack structure will be holding the elements with an array items, and will keep track of the number of elements in the stack with top. Max size will represent the capacity of the stack, meaning the maximum number of elements we can fit in our stack. Let's set the max size to 10, so when we initialize this stack, we allocate 10 times 4 bytes of memory so we can store 10 integers. Okay, now let's implement the push operation. The function will take in the stack to push the elements into, and the value of the element. Let's call them stk and x. Before we push anything in, we need to check if we have enough room. We can do that with a simple if statement comparing the top and the max size of the stack. if the max size of our stack is 10 and we already have 10 elements in there, we wouldn't be able to fit in more elements. So we should handle the error instead of pushing in more elements. Now we can write the part where we push new elements to the stack after the else statement. We will first add value x to the items array after the last element. Top is the number of elements in the items array, so the index of the last element added should be top minus 1. That's why we are adding the new elements to the index top. And after we pushed in the element, we need to increment the top by 1. So that is how you can implement the push operation with an array. Now let's see the pop operation. For pop, we will just pass in the stack as a parameter. We don't need to input anything else because we will always be removing the element that was last added. As I mentioned before, the function will return the value that was popped out of the stack. When we implemented push, we checked if the stack was full, but in pop, we are going to check whether the stack is empty or not, because we shouldn't try to pop an empty stack. So if this function is called, when top is 0, we will handle the underflow error instead of popping an element. And if the stack is not empty, we will remove the last element, which we'll be writing here. If the current stack size is 8 and we pop the last value, we're not actually going to remove the element from the items array. We are just going to decrease the top by 1, so that if later on we push a value into the stack, it will be pushed into the right place. You can see that the value of top defines the boundary of the stack. So if we control the top value, we can control what's included in the stack or not. After we increment the top by 1, let's return the popped value. Because we didn't actually remove the pop value of the stack, we can just return the value of the index of top from the items array. So that was how you implement the pop operation. Peek and isEmpty are pretty simple. For peek, you just return the latest element with top minus 1 as the index, and for isEmpty, you just check if top is 0 or not. So as we can see, this is quite efficient. Every operation is an O of 1 operation. The only issue with this implementation is that there is a max size. So how can we fix that? So we can solve the max size issue by using dynamic arrays, but that would increase the complexity of the implementation. If we double the array size every time it reaches a max, push and pop would technically be an amortized O of 1 and not truly constant time. As you can see, there are pros and cons of each implementation. So far, we have fixed array and dynamic array as implementations. Can you think of another one? Yes, linked list. What would a linked list implementation look like? Let's have the stack ADT have two variables: count to determine how many elements are in our stack, and head to determine the head of the linked list. How do we push items into the stack with this implementation? Without thinking about it, you might say that you can just add to the end of the linked list every time you push, and then remove the last element every time you pop the stack. Let's analyze this, and we can see that this might not be such a good idea. If we remember last time, adding an element to the end of the list is an O of n operation. Why? Because we have to traverse all the way to the last node from the first node so that we could connect the last node with the new node we just created, aka the element we want to push into the stack. You might say, oh, let's just have another pointer, tail. Yeah, that's not bad, and it will allow us to push elements in O of 1 time. However, if we want to pop an element in our stack, we still have to traverse through the whole linked list to remove the last element. So that's not a great solution. The solution is actually to add a new node and assign it as the new head. So when you're pushing new elements in our stack, you don't add the new node to the end of the list. You add them to the beginning of your list. Your head variable will keep changing since your head is always a different node every time you push or pop your stack. Here's how you can implement push and pop with this new implementation. The inputs will be the same as the array implementation. We'll take in the stack and the value to add. Unlike the implementation of a fixed size array, we don't need to check if the stack is full or not, because there is no limit to the size of the stack. So we'll just jump right into the part where we add a new element. First, we need to create a node that has x as its value. And just to refresh your memory, a node in the linked list consists of two fields, value and next. Value holds the value of the element, and next holds the pointer pointing to the next node. Next, we will make that new node point to the head, and then assign the new node as the head of the stack. And finally, we'll increment the count by 1. So that was the push operation. Next, let's see the pop operation. So we will take in the stack as an input and return the popped value. Before we write the pop operation, we have to check whether the stack is empty or not, because we shouldn't try to pop from an empty stack. So we'll use an if statement, just like before, and check if the head is null. If it is, then we'll do the underflow error handling. Otherwise, we'll start removing the element that was added last, which would be the head. Because we would have to return the pop value, let's store it in a variable before we let it go. Next, we will assign the head, which is going to be the second node. The second node can be expressed as stk for stack.head.next because the address of the second node will be stored in the next of the head. So we will assign that as the head of the stack. And finally, we will decrease the count by 1 and return R. So that was the pop implementation using the linked list. Like we just saw, if we push elements as the head, we can push and pop it in constant time without having to traverse through the stack. Great. So you've essentially thought about 4 different implementations, and there is the time complexity for push and pop for each. You can push and pop in constant time for fixed arrays, but the size is fixed. You can use dynamic arrays to solve that problem, but then push and pop will be amortized constant time. If we push and pop elements as the linked list head, we'll be able to do in constant time, and there wouldn't be a maximum stack size. Adding and deleting elements at the end of the list doesn't have that much advantage compared to the other implementation. Great, so this is the critical thinking we want to develop throughout this course. You can also think about how different implementations affect memory space. Most of them have the same space complexity, for example, the linked list and the dynamic array implementation. However, technically, a linked list uses more space than an array, since it has to keep the value and the pointers. Alright, so now you know what a stack is, and the pros and cons of different implementations. I'll see you in the next one.